Hello, ladies and gentlemen, and welcome to a new era of this channel. The beginning of something massive. The most fundamental subject, the foundation of AI. Linear algebra mastery begins. I've been really looking forward to getting into this. I started self-studying math, started abroad, I went to discrete math. Discrete math, I think, is still a great approach. I wanted to go more general. So I bought a book called A Brief Introduction to Mathematics. Ultimately, though, I circle back and decide to start with a textbook, Elementary Linear Algebra by Anton and Call. Howard Anton and Anton Call. Wow, that's quite something. Finally, this is very exciting. Yeah, I've been wanting to self-study mathematics more and more, and this seems like a great place to begin. There's only 9 chapters in this book, and apparently it's very, very elementary, very fundamental, and I believe there's no need for any previous knowledge of really much at all. I think it starts with the most basic things. So just kind of flipping through here. Standard textbook, it looks like. Pretty modern though. Ooh. This is very, very interesting. ChatGPT gave me basically 4 fields to master within mathematics in order to maximize mastery of artificial intelligence. And linear algebra is number 1. Number 2, I believe, is calculus. Then it's probability and statistics. And then discrete mathematics. And so I plan to master all of them. And how do you do that? I don't know, man. Couldn't tell you, but I think the thing you got to do is you got to get started. So I will start with questions. What is a linear algebra about? I think it's studying, I don't know, there's eigenvalues and eigenvectors keep coming up. Vectors and matrices that's definitely a big thing in linear algebra. Eigenvalues, vectors, matrices. What are matrices? Matrices are like grids, right? Something like that, grids, they've got data points within them. Vectors are like, they've got magnitude and direction, right? They're kind of like arrows that they're like direction and magnitude. Eigenvalues, eigenvectors, I have no idea. What else we got? Sequences. Chapter 1 was like sequences of linear systems of linear equations and matrices. Determinants. Determinants have to do with matrices. Euclidean vector spaces. Vector spaces, I don't know. I know Euclid, the Greek, ancient Greek. General vector spaces. Okay. Eigenvalues, eigenvectors. Inner product spaces. These spaces, I don't know. Diagonalization in quadratic forms. Orthogonal matrices. General linear transformations and numerical methods. All right. Okay. So let's just start. Jump in. I'm only going to be doing a few minutes here, and then I have to go get a haircut, and then I'll finish up the few minutes after to get to 25 minutes today. So we start with this first thing, elementary linear algebra. We start with applications and historical topics, and there's a lot. This is kind of just an index, or maybe a table of contents of sort of historical topics and applications. So you got aeronautical engineering, astrophysics, biology and ecology, business and economics, calculus, chemistry, civil engineering, computer science, cryptography, differential equations, electrical engineering, geometry and Euclidean spaces, library science, linear algebra, historical figures, mathematical history, mathematical modeling, mathematics, medicine and health, numerical linear algebra, operations research, physics, probability and statistics, psychology. Would you look at that? How many applications there are for linear algebra? So within aeronautical engineering, you got lifting force, solar powered aircraft, supersonic aircraft flutter, yaw pitch roll. Learned that one in neuroscience. I don't know if that was right though. Astrophysics, Kepler's law, Johann Kepler. Measurement of temperature on Venus. Biology and ecology, air quality prediction, that's cool. Forest management, that's cool. Genetics, cool. Harvesting of animal populations. Population dynamics, wildlife migration. I think I'm really going to like this. I'm not going to lie. This stuff sounds all really cool. Business and economics, game theory. Nice. Leontief. Input-output models. Market share. Sales and cost analysis. Sales projections using least squares. Least squares. Yeah, I feel like I learned that in statistics. Least squares, yeah. It's like modeling like a graph, minimizing the least squares. What do you call that? Like overlaying the graph. Best fit is a best fit model, I think. Calculus, approximate integration. Derivative of matrices. Derivatives? Wait, hold on. Derivatives? Oh, determinants. Okay. Hopefully I don't need to, calculus is in here. Derivatives of matrices, integral, inert products, partial fractions, chemistry, balancing chemical equations, civil engineering, equilibrium of rigid bodies, traffic flow, balancing chemical equations, computer science, color models for digital displays, computer graphics. I've heard, linear algebra is using graphics a lot. Facial recognition, fractals, Google site rankings, warps and morphs, cryptography, Hill ciphers, differential equations, first order linear systems. That's where I'll leave it for now. This already sounds like super fascinating beyond. This is beyond fascinating stuff. Quite possibly the most fascinating thing I've ever read. So we'll get through the applications to begin to title. Cal Poly. Then we'll kind of just read through the table of contents. And then I'll just read through kind of about the authors. And then there's the preface, which I'll read more like, I'll read and then recall, retrieve. This is a short class, 40 lectures. It's only 8 weeks. Maybe you don't have a lecture every day. You have like a lecture and then a work day. Or you probably don't have class 5 days a week. If you have class 3 days a week, okay, then it's going to be 13 weeks. And you got to add tests and quizzes. Okay, sure, this is a full semester class then. Systems of linear equations and matrices. That's chapter 1. So we get pretty quickly into it. But, yeah, I'll talk to you guys in a little bit. But yeah, we're back. Looking a little different. Shoot, I left my AirPods in the car. That don't matter though right now. We're back for more linear algebra. Just set the timer there. Right. So when we were gone, before I left, we were reading about applications and historical figures. We're just going to keep reading through that. So electrical engineering, we've got circuit analysis, digitizing signals, LRC circuits. Okay, not too familiar with electrical engineering. Geometry in a Euclidean space, angle between a diagonal of a cube and an edge. Direction, angles, and cosines. Generalized theorem of Pythagoras. Parallelogram law. Projection on a line. Reflection about a line. Rotation about a line. Rotation of coordinate axes. Vector methods in plane geometry. Library science. ISBN numbers. Linear algebra, historical figures. Harry Bateman. Eugene Beltrami. Maxime Boucher. Victor Bunyakovsky, Lewis Carroll, Augustine Cauchy, Arthur Cayley, Gabriel Kramer, Leonard Dixon, Albert Einstein, Gotthold Einstein, Leonhard Euler, Leonard Fibonacci, Jean Fourier, Carl Friedrich Gauss, Josiah Gibbs, Jean Golub, Jorgen Peterson Graham, Hermann Grassmann, Jacques Hadamard, Charles Hermite, Ludwig Hess, Karl Hessenberg, George Hill, Anton Householder, Camille Jordan, Wilhelm Jordan, Gustav Kirchhoff, Joseph Lagrange, Wassily Leontiev, Andrei Markov, Abraham de Moivre, John Raleigh, Earnhardt Schmidt, Isaiah Schur, Herman Schwartz, James Sylvester, Olga Todd, Alan Turing, John Venn, Herman Whale, Joseph Vronsky. Didn't recognize a lot of those names, but I recognized a few. Mathematical history, early history of linear algebra. That's cool. I'd like to know how this fits historically. Mathematical modeling, chaos. Cool. Cubic spines, curve fitting, exponential models, graph theory, least squares, linear, quadratic, cubic models, logarithmic models, Markov chains, modeling experimental data, population growth, power function models, mathematics, Cauchy-Schwarz inequality. Well, we already read about Schwartz, Hermann Schwartz. Constrained extrema, Fibonacci sequences, Fourier series, Hermite polynomials, Laguerre polynomials, Lagrange polynomials, quadratic forms, Sylvester's inequalities, medicine and health, computed tomography, genetics, modeling human hearing, nutrition, cool, numerical linear algebra, cost and flops of algorithms, data compression, facial recognition, FBI fingerprint storage, fitting curves to data, householder reflections, Liu decomposition, polynomial interpolation, power method, powers of a matrix, QR decomposition, round off error instability, Schur decomposition, singular value decomposition, spectral decomposition, upper Hessenberg decomposition, operations research, assignment of resources, linear programming. That's something I've looked into a little bit, storage and warehousing. Physics, displacement and work, experimental data, mass spring systems, mechanical systems, motions of falling body using least squares, quantum mechanics, resultant of forces, scalar moment of force, spring constant using least squares, static equilibrium, temperature distribution, torque, probability and statistics, arithmetic average, sample mean and variance, psychology, behavior. So lots of applications, lots of historical figures. Linear algebra now, Howard Anton is from Drexel University, and Anton Call from Cal Poly. Got some copyright stuff, publishing stuff. All right, so now we get into the contents. Systems of linear equations and matrices, determinants, Euclidean vector spaces, general vector spaces, eigenvalues and eigenvectors, inner product spaces, diagonalization and quadratic forms, general linear transformations, numerical methods, supplemental online topics, appendix, working with proofs, complex numbers, answers to exercises. Okay. Should we memorize the structure of this book, the 9 chapters? Sure. Why not? What are the 9 chapters in elementary linear algebra? By Anton and Call. So why do I spend the time to memorize chapters of a book instead of the concepts at hand? Oh!
Run this.
Okay. The reason I memorize it's just experimental. It doesn't take a ton of time. It takes a few minutes. But the idea behind it is to get the scaffold, the schema, the big picture of the subject or the resource that I can then place details onto. And so we're going to create a new deck, and we're going to call it Elementary Linear Algebra by Anton and Call. Okay. Then we're going to take elementary linear algebra. We're going to add a new card. What are the 9 chapters of elementary linear algebra? Anton and Call. Yeah, I think it's potentially worth the time to do this kind of big picture memorization and scaffolding. Because then I can say, what is linear algebra about? Well, I can talk about the chapters. Those are the big ideas. So, all right, there's not much room on this desk. So here we go. 1 is systems of linear equations. I'm familiar with systems of linear equations and matrices. Matrices, yeah, kind of. Not too much, but a little bit. I know what they are. 2 is determinants. That's a much smaller chapter. 3 is going to be Euclidean vector spaces. Interesting. 4 is going to be general vector spaces. 5 is going to be eigenvalues and eigenvectors. 6 is going to be inner product spaces. 7 diagonalization. Diagonalization and quadratic forms. 8 general linear transformations. 8 general linear transformations. 9 numerical methods. Cool, add. All right, so here we are. Let's go ahead and do this first card. What are the 9 chapters of elementary linear algebra? Linear systems of linear equations and matrices, determinants, something vector spaces, Euclidean vector spaces, something else vector space, standard vector spaces. 5 eigenvalues and eigenvectors, eigenvalues and eigenvectors, eigenvectors and eigenvalues. 6 sequences. 7, 8, 9 numerical systems, numerical methods, systems of linear equations and matrices, cool, determinants, cool, Euclidean vector spaces, general vector spaces, okay, eigenvalues and eigenvectors, okay, inner product spaces, diagonalization and quadratic forms, general linear transformations, numerical methods. Again, systems of linear equations and matrices, determinants. 3 Euclidean vector spaces, general vector spaces, eigenvalues and eigenvectors. Damn it, what is this thing? Products, something linear products. Diagonalization and quadratics. Numerical methods. What was 8? Linear something? Yeah. 6 is inner product spaces. 7 is diagonalization and quadratic forms. General linear transformations. Okay, again. Linear systems of linear equations and matrices, determinants, Euclidean vector spaces, general vector spaces, eigenvalues and eigenvectors, product spaces, linear product spaces, diagonalization and quadratic forms, linear productization, numerical system, methods, transformations, damn it, inner product spaces, did I say that? Inner product spaces, diagonalization and quadratic form, general linear transformations. Okay, we should have a good run here. Here we go. Systems of linear equations, determinants, Euclidean vector spaces, general vector spaces, eigenvalues and eigenvectors, inner product spaces, diagonalization and quadratic forms, general linear transformations, numerical methods. Boom. Good. Who's got their card getting broken into? Hopefully not mine. All right, so within this first chapter, there's going to be 11 lessons or subsections. You know what? I'm just going to skip reading these like I read the other things, because we're going to get to these at some point, and I don't think exposure really does much. Supplemental online topics. So we got linear programming, a geometric approach, linear programming, basic concepts, linear programming, the simplex method, vectors in plane geometry, equilibrium of rigid bodies, the assignment problem, determinant function, Leontief economic models, working with proofs, appendix A, appendix B, complex numbers, and it's just exercises. Okay, so okay, these are just that section of the book where they say to, what is that section of the book called? To who you're writing to. This book is dedication page. Okay, so tomorrow we're going to start with the about the authors page. Just quickly read that. It's Cal Poly San Luis, live in Santa Barbara, which is an hour south of San Luis Obispo. Then we're going to get into the preface, and then we're going to jump right into section 1, systems of linear equations. Oh, whoa. That's crazy. You can represent systems of linear equations with matrices. Now that's really interesting. Quite interesting. Yes, indeed. Haha, yes, indeed. All right, that's it for today. All right, I'll talk to you guys tomorrow.